Hello. Well, this lecture we're going to move to a completely different philosophy. Right? The previous two lectures we deal with the molecular-based methods. So the molecular-based methods we cover the Hartree-Fock, the perturbation theory MPN, the configurations interactions, and the couple cluster. Right? And it's all dealing with the wave functions and electron wave functions as the functions of the 1, 2, and electrons. So definitely it's size dependent. It depends on the number of electrons. As the molecules getting bigger, they have more electrons, the wave functions bigger and getting more complicated. So the computational demand is going to increase with the number of electrons. In a completely different approach, we call it density functional theory. So in the density functional theories, or for short DFT, the philosophy, if we can express the energy as a function of density, and the densities depend only on the x, y, z in space and the coordinates. So it does not depend on the size of the systems. It, regardless of it is an H2 molecules or a proteins or the DNA of any humongous piece of metal. Okay, so that would be a lot more cost effective when we deal with the macro systems. So definitely there's a certain advantage right there. Okay. So let's analyze it from the Hartree-Fock energy expressions. Right? So the energy of the systems have the kinetic energy, the potential energy from the nuclear electrons, have the electrons interactions, and the constant nucleus that we don't have to worry about, that we have to tag along. All right? So now, remember the density functional theories assume that you can express the energy as a function of density. So let's look at each term. If we know how to express it as a function of density. Kinetic energy, nah, there's no known form. As a function of density. We don't know how to do it. Okay? For the nuclear electrons, yes, there's a class of expressions here. The densities of electrons are in the little cube, right? So there's a little partial chart of densities in space in that cube box there, and it attracts with the nuclear charge over the distance between the center of that cube to that nuclear charge. That terms, right? And then if we integrate over all space of that electrons, then we know that that's the term for the electron ions. Or we can just say that the density is a function of R, and it's better yet, I would say, better yet, we said it's a function of R, and that would account for all electrons as a function of density. Now, electron-electron interactions in Hartree-Fock, it turned out there is two terms. One, they have classical counterpart. This is the Coulomb repulsion terms. So that Coulomb repulsion terms here is the repulsion between the electron I and J. It's just densities, right? Density in the cube, all right, of the electron I times the cube of the I, and the electron density in the cube J of electron J in the space, and the distance between the two cubes. And I integrated all space of dVi and dVj. And that's the repulsion of two electrons. So, yeah, there is a classical, I can write that term, is a function of densities. Exchange only exists when we derive with the Hartree-Fock theory. And this exchange term here is for electron in parallel spins. And that's in fact is the origin for the Hund's rule. Remember the Hund's rule? The high spins with the higher multiplicity or high total spin had lower energy. So these exchange energy terms is a negative. It's a stable term, a stable interaction terms. So unfortunately, these terms have any unknown form as a function of the densities. However, virial theorem saying that the magnitude of the kinetic energy roughly in the same magnitude with the potential energy. And the potential energy is consistent of all of that three terms, which we already know, two major terms already. And the exchange is pretty small. So between the two unknown terms, definitely kinetic energy is much, much more important. Okay, so if we want to do anything approximate, we need to be accounting the kinetic energy as accurate as possible. Well, previously people have done different approximations for the kinetic energy using like uniform electron gas model. They all fail. They predict the molecule doesn't exist, so that's failed miserably. Not until Kohn and Sharp have come up with a very genius idea. And in fact, for that idea, Kohn got a Nobel Prize with John Popper, who developing molecular base in 1998, Nobel Prize. Okay, so what Kohn and Sharp does is assuming the molecular systems as an independent electrons. Each moves in an effective potential that is similar to the centrifugal approximation that we had used in the Hartree-Fock theorem. So now in that case, the approximate Hamiltonian H naught here is just a sum over that effective one electron, sum over term, I term. So this kinetic term of the electron I and the potential of electron is sum over all electrons. And this is separate, independent electron, we can solve it accurately. If we approximate the wave function as a single slider determinant, just as in the Hartree-Fock method, so this psi naught is single slider determinant, then we can solve these Schrodinger equations exactly. We can solve that. Okay? And we can solve for the exact solutions. When we get that slider determinant, and that is in fact we solve by the fact is that one similar to the Fock operators. So we have these individual electron i's here operated on the spin orbitals I equal to orbital ij. Okay, so this is an eigenfunctions problem for one electron, similar to the Fock, to the Hartree-Fock methods, and we know how to do that, like a hydrogen atom-like. So that's solvable. When we've done that, we have the solutions with the single slider determinants. We can calculate the kinetic energy by just plugging in the kinetic energy operator and calculate the average for that. Quantum mechanics principle tell you how to do that. Where the density, we just sum over all all the densities of electrons in all the orbitals. So simple. So what is it? Well, Kohn and Sharp borrow the molecular orbital concept, the Hartree-Fock theories, to approximating the kinetic energy as accurate as possible and leaving these small corrections. Well, what is correction? It's a correlations energy. Remember Kohn and Sharp starting out with assuming that these are independent electrons. So correlations energy is not in here. So it's leaving that remains some unknown form. and we'll see how we can approximate that form. We coincide approximate a way to calculate the kinetic energies using the independent electron case and molecular orbital framework, Hartree-Fock base. We can calculate the approximate kinetic energy term as accurate as possible. So what it is that we just leave the difference, here, which is the correlations energy, and the exchange term, and we can group them as an exchange correlations energy term. EXZ is usually we denote it, right? And this is the unknown. So now see this. This energy is fundamentally exact. We have not made any things. See, this is correct, right? It's just we don't know the term for that. So this term is still fundamentally exact. The beauty is here. He introduced T naught, he subtract T naught. And he has, Cohen Sham they have a way to calculate this accurate. So now these small terms here remain unknown. Form. So, well, one thing is that it's a function of the densities and it's a universal functions. It's independent of the molecular system. So once you design that functional form, you can apply for small molecules, atoms to the solid or proteins. Okay. The only issue with this is we really don't know a form for that, and have no ideas that much. So as I mentioned, it's still fundamentally exact. So so the Dft method, remember it's related over here, is have the MO framework in there. So the computational cost similar to the Hartree-Fock theory. However, because it including electron correlations in the EXC terms here, whereas the Hartree-Fock does not. So it does have more accurate, it is more accurate than the Hartree-Fock theory, and by experiments, it is similar to the second order perturbation theory in accuracy. The only headache when dealing for the practitioner, when dealing with the density functional theories, is that a different approximation and parameterization procedure often lead to the different EXC functional and different functional form establish a method. And currently we have about 200 and some form for these EXCs. And in communities, in the quantum chemistry community, we have the terms like DFT zoo. So for practitioners who just want to using a DFT methods, sometimes can be a little bit of frustrations in trying to getting to know which DFT method should be best to use. So there are a number of assessments out there, and there's a number of popular methods, for example, known in the communities, such as a B3-lip method has been decent, accurate for many chemical properties. So to these points, I have covered very much all quantum chemistry method. So we need to have one more lecture is to go back to addressing the MO approximations, the LCAO approximations. So the basis set method, which for the last lecture, lecture number 4.